Okay, so we're thrilled to have Cecilia Garraffo. So she was originally from Argentina and got her MS in astronomy from La Plata National University, after which she got a PhD from University of Buenos Aires. And during this time, she focused on general relativity and extensions thereof. And after she continued her work on theoretical physics and cosmology at Brandeis University. Then she joined Harvard Smithsonian Center for Astrophysics, where she worked on computational stellar astrophysics. And in 2018 became part of the Institute for Applied Computational Science at Harvard. And there she developed machine learning algorithms to conduct data-driven astrophysics research. And so currently she is the founding director of Astro AI at Harvard Smithsonian Center for Astrophysics. And this is a research institute for advancing astrophysics through artificial intelligence.
Thank you so much. Thank you for the kind introduction. And do I need a microphone or is that okay?
It's
okay, cool. I'll try to speak loud. Oh, I see. I see. It's technology. Okay. Well, thank you so much. Thank you for the invitation. I love to visit NYU. I cannot beat the place or the city. So I'm very excited to be here. And I'm going to be talking about how we can leverage AI to transform to transform this data revolution that we're entering in astronomy into a discovery revolution. Yeah. Okay. Sorry. This is work in collaboration with Astro AI, which is the research institute that was just mentioned by, sorry, by Monica. And that I am the director of, but it has a lot of people, so it's all work in collaboration with all the group. And what we do at Astro AI is we develop AI and machine learning models that are specifically for astrophysics research. I keep going the wrong direction. So yeah, so as I said, we're about to enter a petabyte era in astronomy with the new generation observatories and the next generation. Some are operating right now and some are coming soon. We're going to observe more data in a year than we have so far. I have to figure out which way to go. Okay, so going down is the right one. Sorry. We're going to observe more than a year than we have observed so far in all our history combined. For example, this is the Vera Rubin Observatory in Chile that is going to open its eyes very soon in a few months. And we're going to go from observing, this is the supernova detections evolution in time. We're going to go from observing a few thousand a year to observing 1 million a year. We're also going to have 10 million alerts for supernovas, for changing things in the sky. Vera Rubin is going to observe the changing sky. It's going to take differences between the sky all the time that you can see differences in brightness of stars. Some of them would be supernova. We're going to observe more than 10 to 100 million of AGNs. So this is going to be a very different regime for doing research. And this is just one example, but this is going to happen across the electromagnetic spectrum. We have new generation telescopes coming online. Some of them are online already. Some are coming really soon, and we will have this revolution across the electromagnetic spectrum. In addition, we have now new domains and new ways of observing the universe from the Event Horizon Telescope that can observe very small details, so a crazy good spatial resolution very far away, to James Webb that we can observe for the first time molecules in atmospheres of planets around other stars, exoplanet atmospheres, and that blows my mind. The Event Horizon Telescope can observe a resolution that is like looking at an atom and at an arm's length. And for the first time, we can observe with no light. For example, with gravitational waves. No, sorry, again. Okay, there's a video that is not playing, but with gravitational waves, we can now touch the fabric of space-time itself, and with IceCube, we can observe neutrinos. So there's all these different domains. And across these different domains, we also will see such a crazy increase in data. These are the expected detections of gravitational waves with time. So we're going to be invaded by data. And we're not ready. How are we going to process or analyze or make sense of these amounts of data? Definitely not in the way we're doing astrophysics right now, not with the traditional methods. We just have to change the way we do research. And artificial intelligence can help. Every time you see big data, you typically think of artificial intelligence, and it can help process these massive amounts of data to begin with. But not only to process them, but what I'm most excited about is artificial intelligence, unlike traditional methods, allow us to intentionally search for the unexpected, for the things that we don't know are there. We have not done that before. We find things by chance or things we're looking for. Let me give you an example. Imagine we have a lot of astronomical data that is unlabeled, and I'm showing images here, but could be any kind of data and a lot more than the ones I'm showing. Imagine in this petabyte era where we get lots of data. We don't know what data is. You can do the most simple AI exercise or machine learning exercise is unsupervised clustering, and this data will get organized in clusters. It will get organized according to similarity. But the key thing here, it's not a similarity you impose. You don't need to know the metric by which these things are similar. They're going to just be clustered by similarity, any similarity. So now let's look back. Once you organize all these, because you cannot process all these amounts of data, then you go back and you look at each cluster and you're like, you'll say, okay, I expect this to be clustered together because these are exoplanet transits. These are supernova explosions. These are galaxies. These are stars. But now let's do this exercise of going 50 years back in time and imagine we have not yet detected any gravitational lensing events. We don't know what these are. And these are rare enough that in the data before, we would throw them away because it's just 1 in a million observations. So you don't see a pattern there. But when you go back and look at them all together, the pattern is immediately coming out. Like it's so easy to see that we're missing something, but there's a pattern that we have not seen before. So in this way, we could have discovered gravitational lenses intentionally, even without looking for them, instead of by an accident that took 50 years to happen. And so now imagine we have all these data clusters that I just showed you, but more generically, just clusters of data. And we have right now some outliers. We have plenty of outliers in astronomy that we don't know what to do about. We can go look at each of them with more careful detail with our telescopes. So there are just too many. And in a time when we're going to get so much new data, this is going to change. Some of them are no longer going to be outliers. They're going to be in their own class. Similarly to what I said could have happened with gravitational lenses, we were missing them because they were like outliers. And now you see a lot of them. And so if we go back and forwards with this, some new outliers will come up that maybe it is just because we don't have enough data. Maybe it's a data glitch, maybe it's an instrumentation issue, or maybe it's a new class. And so we're going to find a lot of new classes, I am pretty sure. Things that we thought were outliers and now they're their own class, and new outliers that some of them will point to new classes. So all very good, great. Hopefully I convinced you AI is useful, but it's not as simple as usual, right? Why do we need new AI for astronomy? We could just go and apply AI and everybody's happy and we make all these discoveries, but there's a couple of reasons why this is not so simple. So one of the reasons is astronomical data is very different than the data that these models the state-of-the-art models have been trained on. For example, astronomical data is very biased. We only have one perspective of the universe because we're passive observers in the universe. Well, maybe we have a couple, but typically you cannot go and look at the other side of the supernova explosion. So we have biased data, we have multimodal data, many different bandwidths that we observe for explaining the same phenomena. And sometimes also photometry, time curves, like light curves or time series, to point at the same phenomena. State-of-the-art models are not built or optimized for this. In addition, they only take like red, green, and blue if you have an image. They don't take spectral information. They just don't work. They're not meant for this. We have a lot of incomplete data, massively unlabeled data. So the data is challenging, but the other reason is the task. Machine learning and AI models have not been optimized to extract physical information, to understand. We don't want to reproduce the universe, we want to understand it. If I could predict when is the next supernova going to explode and where, it would be great. But if I cannot say why I'm making that prediction, then it's not physics, right? So the typical state-of-the-art models are not meant for that. And so that's why this means that we need to shed light in any black box for it to be science. So that's what I have been focusing on and what Astria has been doing, and I can give you a couple of examples about physical models and what I mean by them. So this is an X-ray binary. This is an illustration. It's not the data, but the idea is there's a black hole and an evolved star. So a regular star, a sun-like star, it could be, that is losing mass onto the black hole. The mass is accreting on the black hole, and this star gets less and less massive. But anyway, this material gets very hot and it emits an X-ray. So we call these X-ray binaries. But the data looks like this, the spectrum, not like the illustration, right? And so if you want to characterize a system to get this decomposed in different contributions to this emission and understand the system, get the physical parameters in it, for an expert on X-ray binaries, it will take 10,000 of these spectra, 24 hours of work or so. So the first project we did with Ethan Trujillo was our first Astrea student, he built a machine learning model for fast fitting of X-ray spectra. What we wanted to do was to characterize these systems faster. So what he built was an autoencoder. And this is, I can explain a little bit what this is. The idea is so an autoencoder, all these things you see here is a neural network really. And each thing you see here is a layer, and different layers have different flavors. They're different kind of nodes and networks, but it does not matter. The main thing is this is a whole complicated mathematical differentiable function with a lot of parameters. And the task is, if I give this model some data, I expect the model to give me as close of the input to the input as possible. So just don't do anything, give me the input, which seems straightforward, except the catch is it has to go through a very heavy dimensional reduction. And so if you're able to reproduce the input from a much smaller dimension, it means that you have extracted the important information in the system. Just like if you have a list of X and Y's that describe points on a line, you can reduce it to a two-dimensional space of the slope and an ordinate, right? You would expect this to be extracting what's important. The problem is we can do that and reproduce the input very well, but the problem is that the code, which is this red box, the small dimensional space, is typically uninterpretable. It's non-physical. It's not going to be the slope and the ordinate. It's going to be something in a representation in some basis that we cannot interpret easily. We won't know what that is. So we cannot make use of that. That's in typical machine learning models. But the cool thing was that Ethan was able to build and train a model that guarantees to have the physical parameters. And how? That's what I call a physical model, right? This gets us closer to the task we want to do. So if you're curious how to do it, what we did was we have a way to simulate this data. So we start from the physical parameters, we simulate the spectra with something called expect, and we train an emulator that is the decoder. We train the emulator because simulating the spectra is too slow for putting it in a machine learning model that we're going to train. So once we have an emulator, what we do is we plug in the encoder, the one that is going to do the dimensional reduction. We freeze the decoder, sorry. Okay, so we freeze this decoder, and then the encoder is going to be trained. So we're going to train this end to end. Input to output, we compare the input to the output, and we train this model until it reconstructed it well. But if we cannot train this part of the network, the encoder is going to be forced to match the physical parameters that are the best ones to reproduce this data. So then what we use is the encoder, and from real data, we can extract the parameters, the physical parameters, much faster. So these work very well, and actually I can show you the decoder to get an idea of if with the physical parameters that you extract from a particular spectrum, you use those to reproduce the spectrum with XPEC or the decoder, then this is the match you get. This is a typical match. So you do a pretty good job of fitting. And this model does what the 24 hours of work that an expert was needing to characterize the system in less than a second. Another example for physical models that we tackle is in exoplanet atmospheres. So here's the deal. We want to understand the composition of the atmospheres of exoplanets. And now for the first time, as I said before, with James Webb, we're able to do that, at least for nearby planets. And how we do it is we observe the light of the star. We take a spectrum of the light of the star without the transit of the planet. And then we observe the star again when the planet is transiting. And so the difference between the light, the spectrum, this spectrum and this one is going to be the absorption lines of the atmosphere of the planet. This absorption has information about what is the molecular composition of the atmosphere. Okay, so if we have the molecular composition of the atmosphere and we have the temperature and the pressure, we can model the spectrum. We can model these differences. We can say what is the absorption, what are the signatures of these molecules. But what we're interested in, and this is the typical case in physics and astronomy, is the inverse problem. Given the spectrum, can you tell me what is the chemical composition, temperature, and pressure of this planet? And so we could do play the typical game that is simulate this for a bunch of different conditions, but it's very much like throwing darts until it's hit or miss, right? You can do MCMC, but that's really expensive. And so we can use the same idea of this physical model that we developed before and train an emulator to do the forward process, the forward modeling, and then just freeze it and plug the encoder in, just like we did before, and go from the data to the chemical composition. And we tried this. So another interesting thing, I think, is when you build models for these kind of models for astronomy, typically they're applicable to different, we have the same problem over and over again in different, from exoplanets to X-ray binaries to cosmology, they are applicable to different domains in astrophysics. And so we took the same model that Ethan had built, and Mayel, who was our intern, trained it on this exoplanet atmosphere data. And in 2 weeks, he had it to work this well. That's the spectrum, that's the reconstruction. It was really good at predicting the right composition. Now, Ethan spent like 8 months building the model, but this took us 2 weeks. Yes, go ahead.
Can you also validate this approach with tabletop experiments where you create a cell with a mixture of gases and just do conventional tabletop spectroscopy?
Well, yes, actually we can, and we use Hytron, which is so Hytron is a very large molecular database that happens to be at CFA. We're lucky that we have them in-house. So they do that for us, and they do experiments and they do simulations. And so we have used that for training mainly. But yes, in principle, you can build a gas and try to extract this information. But so here, the reason we didn't do that here quite yet is because of the following. This is a good answer. This is maybe the best answer for the data, but it's not the only possible answer. If you look at, sorry, it doesn't matter, that's how well it's predicting. But if you look at the data, this is typical Webb spectra, transmission spectra, right? You get the transmission spectra and you want to see what molecules are present here, but the error bars are pretty large. So if you're a scientist doing this, you don't want the best answer, you want all the possible answers. And so that might be the best answer, but we want that one too. That is perfectly possible as well. And so for that, you want a probabilistic model that will give you the probability of different abundances of each molecule instead of just one answer. And so that brings me to probabilistic models. So we want to build physical probabilistic models. So what we did for this project was to train a normalizing flow. So a normalizing flow is this machine learning technology or method that takes you, it is a pretty clever idea. It takes you, if you can go from an arbitrary distribution to a simple distribution, like a Gaussian, but anyone you choose, with a set of invertible functions, then you can eventually invert these functions and go from the simple distribution that will be your prior to an arbitrary complex distribution that in this case would be your posterior probability distribution, the one you're aiming for, right? Now, okay, this sounds very simple, but if I know posterior, why will I need this, right? If I know the posterior to go from here to here, then I don't need to invert it. But this is for training purposes. So what you do is you train a neural network. Oh no, I went too far again. Okay, you train a neural network. So you choose the functions. Functions are typically a very simple, like a spline function, very simple functions. What you don't know are the parameters of these functions. And so what you do is, given a spectrum, you get from a neural network a set of parameters that will take you from this prior to this posterior. So you train these on a lot of data that you know the posterior for, and then you're learning how to go from prior to posterior. So this is what we did for this problem to get a, well, just by chance, and I have to say this about the student, otherwise I would be a really bad supervisor. So just by chance, when we were trying to do this for JWST, Ariel, that is a European mission that is going to be launched in 2029, I think they keep delaying things, to observe 1,000 exoplanet atmospheres, had this challenge. They asked the AI community for help building exactly a model like this, to be able to give you abundances on 5 molecules from spectra in a fast and reliable way. So yeah, Mayo won this challenge. But what's more, to be more impressive, is that the challenge was rating us on the marginals. So they gave us, you had to predict radius, temperature, and 5 molecules, right? And then they rated us on how the posteriors of each molecule or each parameter looked, but really each of them independently, but really they depend on each other, right? And so what Mayel did is he built the normalizing flow with all the independent normalizing flows to win the challenge, and then he built the better model for science, which is a unique normalizing flow that gives you the posteriors on all the parameters at the same time. And so Mayo is super bright, but I want to highlight that in my experience, that the success of these kind of projects are based on a very interdisciplinary group. So it's really good to have everyone in the same room to tackle a problem, because astronomers try to do a lot of machine learning and neural networks, and we can do well enough, but there's a whole discipline out there building new models that are better, that are more better optimized. And so it's always good to have everybody in the room. So in this case, we had Mayel, we had Ethan, that was the student who built the previous model. We had the AI experts, we had people in between, like the Astro AI people, spectroscopists, these are the ones with the high trend database, and the astronomers. And an example is, at some point I remember the modeling people, Mayel and the AI experts, were saying, why can't we get such a tight prediction on radius of the planet? Why with the data of the challenge we cannot get that? And then Jeremy Drake here, an astronomer, said, oh, because there's a formula for that. With the input values that they are giving you, you can calculate it exactly. And that's what, so I think it's important to have everybody working together every week. And so for that, I think we need to train the next generation of interdisciplinary researchers with this kind of environment, and train people to know how to how to how to conduct interdisciplinary research. We're building a community at the CFA. Everybody's welcome to join. They're hybrid, these meetings on Mondays, or visit us. But I think NYU has enough resources and computer scientists and the Data Science Center and the CCA that is a very good opportunity to do this research here too. So I talked a lot about simulations so far, because in the two projects I described that are physical, we relied on understanding the physics behind it, right? We were making them physical by simulating things and teaching the model how the data, how the analysis of the data really goes when you do it with physics. Let me now talk about AI simulations, about physical simulations, and in particular how AI can help. I'm showing here a cosmological simulation from the CAMELS collaboration here at CCA. So simulations in astrophysics are really important because most of the times we cannot predict the complex phenomena, even if we know the physics that is ruling the systems. We need to do simulations to be able to interpret our observations. We need to know what to expect to be able to perform inference on observations, but they have problems. Let's start this one again. I guess. The couple of problems that we typically have with simulations are that they become intractable. So they're very expensive many times in this case, for example, and that because they're intractable or not intractable, but very expensive, they often rely on a lot of simplifications. So you have to, you lose some accuracy because of simplification. For example, black hole feedback in this simulation is really important. And yet you cannot resolve the simulation of a black hole, which would be a GRMHD simulation inside of each point here where you have a black hole. You cannot simulate both things self-consistently. You have to use an approximation for the black hole feedback. So going to the black holes. So that is a good example. The black holes, this is the image released in 2019 by the Horizon Telescope. I assume everybody saw this image. And the problem is that simulations for this image, well, the problem, I mean, I think we were all shocked how similar the image is to the simulations that the Horizon Telescope have been showing for years. But the problem is that these simulations that are GRMHD simulations are super, super expensive, and we only have a few. For each configuration, we have 5 simulations, 5 values of black hole spin. Black hole spin is the important quantity here that we'd like to do inference on. The problem is when you do those, you get different outcomes if you have good resolution, which for the simulations, of course, you have for different values of the spin. But when you degrade it to the resolution of the observation, it's really hard to tell what spin that would be, right? There's not a real degeneracy, but in this resolution, it's almost a degeneracy on what is black hole spin. So for that, actually, neural networks are really good at picking up on subtle correlations that are not obvious to the human eye. And so we tried seeing if we could take these images, the simulated GRMHC images, and build a model that will predict black hole spin. And that was Tao Sui. He was a master's student in computer science, and he trained a simple model that does incredibly well, does pretty well for not being able to tell. Now we can tell, this is the predictions, and this is the true values, and if it's perfect, it will be a diagonal. So in these lower values of spin, there's some confusion, but not too bad. And that's reflected here. This would be a diagonal. This is the confusion matrix. And so the limitation here is that we only had 5 values of spin to train on, and that is not great. So actually, we train on 4, we remove 1, and we went to predict that because so that we are sure we're doing things right. So it's really not a lot of simulations to train on. So we built a generative model to try to mimic the GRMHD simulations to see how it worked. And now I'm sure I'm getting a lot of more skepticism in the room, but I'm going to address this. So bear with me for a little longer. So Anya Moran, another master's student in computer science, did this project. to train a generative adversarial network. At that time, those were the state of the art in generative models at WGAN. That the idea is you have a network that will generate fake images, and a network that the task will be to distinguish between fake and real. So you train them together. And how you train a machine learning model is you have a loss function that you're trying to minimize. And so the one that is doing the worst is the one that is going to contribute more to that loss function, and is the one that the model will focus on reducing so that it can do better. So when the generator is not fooling the critic, it will focus on the generator and make it make better, more realistic images. When the generator is too good for the critic, it will focus on the critic, making it a better critic. If you play this game well, eventually you have a very good critic, and the generator becomes very good at fooling, as good as you want almost. And so we build this model, Anya did this model, and so now we have different values of spin that we don't have from GRMHC. And I know we have to take this with a grain of salt and be very careful when we do these kind of things. I'll come back to these, but let me challenge you. Two of these, I don't know why I get the cursor there, but anyway. Two of these are GRMHC simulations, and one of them is generated by the model that Aria trained. Can you guess which one is? Look at it, and who thinks the first one is the AI generated? Second one? And the third one? Well, I think we have like 7, 9, and 8. So it's pretty hard to tell. But you guys are pretty smart. Yeah, it's number 2. And when you look at those, I'm gonna come back to this. Why you could know that it's number 2. And because experts in this kind of simulations can immediately tell you that it's number 2, that's when I get concerned, and I'm thinking, what are we doing wrong? And how can we build a model that is really getting the physics right, and not just fooling the human perception? I'll go back to that in a second. But so so let me continue on the generative path, and then I'll go back to the physical path. So generative AI for astrophysics. The model I just showed you, GANs, that was the state of the art a few years ago, but now in generative models, the state of the art are diffusion models. If you've seen all these very realistic images, well, mine is not very realistic in the sense that is a cat writing an astronomer, but they do look realistic, right? I don't know if anybody here tried DALL-E. That is like the ChatGPT image generator. These are really good, and this is because they use diffusion models. Let me tell you. So a diffusion model, what it does, and I'm showing you an astro example that I'd like to talk about, but typically you have a cat or a dog here for most examples, is if you have an image, in this case it's a dark matter density field, you will degrade it step by step, adding a little bit of noise at each step. So these steps on the top take you to the next point with a little bit of noise until you get to a point which is pure noise or very noise dominated. The trick is with a neural network at each step, you're going to learn the denoising step. So to invert this step by denoising, you're going to learn how to do that with a neural network. You do it for enough images and you get very robust neural networks denoising this function. Then you can add a condition to this that is here, in this case, the stellar density, the baryonic matter field corresponding to this one. And then the end product is you go from noise to this image with a condition. So this is very useful. These are very good, they perform very well. And this is very useful for many things, in particular for astrophysics. This is a 3D version of that. You go from noise to a dark matter field. that was learned from real cosmological simulations. And why it is useful, I'm not treating you this as not a challenge, it's just, this is the stellar field, this is the dark matter field, all of the same simulation. You run a simulation, and these are expensive, you get dark matter and baryonic matter, and then you go compare the baryonic matter and hope it matches your universe. And if not, you start again. In this case, what you can do is, if you train it on a lot of those simulations, what you can do is infer the dark matter field directly from the stellar field, so from an observation. So this cuts computational times dramatically. And you can trust it more or less. This is actually a probabilistic model. It's not going to give you just one realization, but a lot of realizations with different probabilities. And this is a case where I think it's useful to use these tools, because you can say, yes, maybe I trust the physical simulation more, but you can really not do this with the traditional simulations in the same way, right? It does get a lot of the job done. But it goes back to my problem that I said I would come back to this. It goes back to what has been something that I've been worried about, is these diffusion models, all these generative models, are trained and optimized to full human perception, to look realistic, so that when I quiz you, if you don't happen to work in the event horizon telescope collaboration, or even if you do, but you're not looking at GRMHD simulations all day long, you won't know which one is right. But the AI generated doesn't have to be physical. I showed this image to many people, and it's hard to tell, except when I showed it to Daniel Palumbo and Shep Dolman. Both of them are in the event horizon collaboration, and they both told me immediately, it's number 2. I said, how do you know? Well, if you have a photon ring, that is a very important feature of this image, you either have it resolved like here or not. But if you have it resolved, it has to be a perfect circle. So this is not a perfect circle. Now, how are you going to train a model to know that? How are we going to penalize the photon ring? We can add a penalization for that. But how many things are we missing that are not obvious when you look at it? How many physical things that should be happening all over are we missing, and are we not able to reproduce in a physical way? So that's something that I've been thinking about a lot. And this is another example that is a challenge we had at the WS last year. This is an observed solar spectrum, and one of these two is simulated with the traditional methods, and one of these two is simulated with AI, is AI generated. And we had this little AI WS booth giving these challenges to do a raffle and get a prize, and people were excited, but they were like, no, this one is stupid. I don't want to do it because they look the same. Nobody can do it. So right then and there, fortunately, Yuli Gordon, the head of Hydron, the one that is a spectroscopist, passed by, and I said, Yuli, come here, please tell me, which one do you think? And Yuli was sweating. He was like, I have to get it right, but this is really difficult. He told, and I'll tell you, the number 2 is the AI generated. Yuli knew, because he said, if this is synthetic data, there should be no blurriness. And well, now I don't know, 2 or 3, whichever one is blurry, this 3, whichever one has some blurriness, there's no reason for that if this is physically simulated. So that's the AI generated. How are we going to get all that in our models? So now I'm trying to convince you, generative AI is not good enough. We cannot trust it. We can get an approximation, but we have to do better. And that's what I've been thinking about a lot. Like, you cannot, like, this is what happens with generative models. Things go wrong, right? You get things that are non-realistic, that don't conserve energy or mass or any physical quantity. So what can we do to get physical simulations? There's some good examples of physical models, like this is one I particularly like, is Lagrangian neural networks. And the idea is, if you have a system, in this case a double pendulum, and you simulate the evolution of the system over time, now imagine you could know or not know this Lagrangian, but you have a system, you can use a neural network, a vanilla neural network, to go from position and velocity to acceleration, and then evolve the system over time. And you do get you can get better and better networks to do that, but eventually you will lose energy. because there's no constraint to not lose it. It's just learning it from the data. But if you go far enough in time, you're going to lose energy. This is a very cool trick that is from the same system, from Q and Q dot, build a neural network to learn L, the value of the Lagrangian. And from there, derive the Euler-Lagrange equations of motion and get Q dot dot from Euler-Lagrange equations of motion. Because neural network is differentiable, so we can take all these derivatives. So that's the cool thing. And so if you do it that way and you don't, like here, we don't have a term that is the partial derivative of L with respect to time, that's implicitly assuming that this Lagrangian does not explicitly depend on time, then you will force this system to learn a Lagrangian that is independent of time and conserve energy. And you can show that you do conserve energy if you do it this way. So this is really cool, right? Because this model you could trust, I think, or at least you could trust a lot more. You're not going to have someone say, oh, this is not a circle. You will have a Lagrangian that you will learn. However, you will have to do this for each system. This is not generative. This is not generative AI, right? You have a system, you can learn the Lagrangian. Also, they're very difficult to train because you're training on second derivatives of the function you want to learn. There have been other attempts that are different, completely different scope that come from the generative AI world. This is Katie Bowman's group in Caltech. And the idea is, if you're trying to learn a generative model on some systems that have a constraint, a physical constraint, for example, you conserve energy or the mass or whatever, those systems will probably fall in a manifold. If you put it in some kind of representation, you can put them in a manifold that will have edges. If you use a diffusion model, but then you will typically get samples right outside of that manifold, right? Because you're not, like in the other case, you're not exactly conserving energy, you're going to be close, but not exactly within the manifold. And so what you can do is build a mirror map that is, okay, let's do the diffusion, but then let's map it back to that manifold and only take the samples that fall within that manifold. So that's cool, but you'll have to know the constraints. You will have to understand the equations that rule the system, and you can just impose these are soft constraints. So this is pretty good. But what I'm thinking a lot about and what we're doing at Astro AI that I'm not going to talk much about here because it's work in progress, but hopefully next time, is can we get the best of both worlds? Can we get generative models that have a Lagrangian or a Hamiltonian or that we can trust? Can we make them physical? So that's what I'm mostly interested in. Okay. Okay, so I'll briefly describe another thing that is interesting and might be useful for people that is called transfer learning. When you build a model for some domain and some task, can we use it for different domain and different task? So I'm going to talk about it is much more general, but for example, if you have Gaia, that is a space mission looking at photometry of millions of stars, can we characterize the stars from their photometry with Gaia? This is big data again, right? So what you do typically, if you're an astronomer, is we love the HR diagram. This is a diagram that has in the x-axis the color of the star, which is intimately related to the temperature of the star, the effective temperature. And in the y-axis, the magnitude, absolute magnitude, how bright is the star basically, or the luminosity. And so then we also know stellar evolution pretty well, and we can, we have MESA models, we can simulate the evolution of any star with any initial mass and any age, like throughout its evolution, and put it on this plot. So what we're doing here is for different stars for initial masses of different initial masses. This is H, the color is H, and they move through the HR diagram in different ways. Like they come down here, this is the main sequence where they spend most of their life, and then they go up in the red giant branch, and then they go through this evolution. We know that. But the problem here is, so if you're an astronomer, you will take an observation, place it on this HR diagram, and hope to find the right track. Say, okay, which mass does this correspond to? Well, which track does it fall on? But it's really hard for many reasons. One of the reasons is this mapping is highly nonlinear in age. You see that very fast stars go down this path and then they stay there, they change color dramatically without moving in the HR diagram. So it's really hard to tell the age of a main sequence star because they just stay there in that point for a long time and then they go very quickly through other parts. So it's a nonlinear mapping. So that makes it difficult already to tell what is the age of the star. But also you have confidence variations. If you want to predict what mass and age a star is when it's here, it's much easier than here because the tracks all overlap. So you have confidence variations. And on top of it, in some areas, actually, when you put all the data here, in most areas, you have a degeneracy. Is this a young star before the main sequence that is coming down this track, or is it an older star of a different mass that is going up in the background? So neural networks are very good for that. And I'm not going to go into the detail, but for nonlinearities, neural networks are really good. So we build a hierarchical model that has neural networks, but has like Bayesian neural networks that give you posterior probability distributions. We break the degeneracy building two models. So you get the values on that HR diagram, luminosity and temperature, you split it into models, you pass these through two models, you get posteriors on mass and age of each model, and then you combine them in a smart way, taking into account how likely it is to have that age and that mass in this universe. And so we did that, we trained it on synthetic data, this kind of data that I described before, and we tested on a different set of the same synthetic data. And of course, we do really well, 98.3% is really good, it's a fast way of characterizing stars, great, we're all happy. And then we said, okay, let's look at an observed data set. And of course, we're not going to do great, right? On top of it, this observed data set, we chose it because it had good age estimations with a full MCMC probabilistic model, but they used different synthetic databases for isochrone fitting. So there was systematics we knew from the get-go. And on top of it, there's observational error. So we did better than we expected, 88.8%, but it's much worse than synthetic data. So what can you do? If you have in traditional machine learning, if you have two different domains, in this case simulated versus observed data, and you have the same task, you need to build two models from scratch. With transfer learning, what you do is you take advantage of what the first model learned, and you transfer that, and you just train it for a little more on your new domain in the same task. The first model that we built on synthetic data was trained nonstop in a supercomputer for 2 weeks. And then, so what we did was we took the new data set, and in my laptop, that is not great, in 2 seconds, we trained it a little bit more. You can see how the data has the same shape and moves a little bit. It's kind of calibrating a data set. And we went from, in these 2 seconds, we went from 88.8% of the predictions being consistent with the data to 97.8. So I really encourage everyone to try transfer learning instead of starting from scratch if there's a model that is similar to something you want to do. Okay, now Anya Phillips, who's a new Harvard student, is working. She's been working with us before on, so we did this for this observed data set, but it's not so general. And so she's been building this more generalized data set that makes sense with ISO benchmark stars and putting more emphasis on the ones we trust better. So putting in there the confidences of each measurement to build this new model with transfer learning. And then the last thing I want to discuss is what if you have a completely different domain, but a very similar task and a very similar data set? You can use domain adaptation and transfer learning, or a combination of both. And this was something very cool that happened maybe 6 months after starting AstroAI. I realized that astrophysical observations, this is an example of a synthetic data set for cosmology and X-rays, are many times hyperspectral cubes, right? This is an image with high resolution spectra for each pixel. So you have the image in different bandwidths. And that is the same kind of data that you have in remote sensing of the Earth atmosphere. Not only is the same kind of data, because you get hypercubes with high resolution spectra, but also you have the same task. You want to extract physical information from the data set. So that was very exciting because we have at CFA, there's two satellites looking at the Earth's atmosphere, one called MethaneSat, one called TEMPO. MethaneSat is detecting methane plumes in the atmosphere. Methane is one of the two, if not the one, number one driver of global warming. So it's really important, and people are very excited about these detections. And TEMPO is monitoring the pollution in the atmosphere in North America with a very fine resolution of 1 kilometer by 1 kilometer. So these are two very important science topics, I believe, because we're running out of time, to mitigate or help take care of climate change, preserve the planet. Things we're doing with them are, for example, for satellite, for remote sensing, it's really important to detect clouds and shadows because those affect the quality of your results. If you have spectra, you need to know if that spectra comes from on top of a cloud or if it is looking at a shadow, because it changes the results. So the way they do it right now is in MethaneSat, in many satellites, is they do that by looking at an image. Now remember, we have almost 2,000 images because we have high resolution spectra, but they look at one image and try to figure out which things look like clouds and shadow and throw away all that data just to not contaminate. So of course you still have bad data, and you are also throwing a lot of good data away. So one of the projects is we took all the spectral information here and not only improved had a really good detection of clouds and shadows, like here's a shadow is gray, no shadow is white, and the red line gives you the prediction of if it's a cloud or a shadow. It's really good. But not only that, but we are able to correct the spectra pretty well for shadows. So I think there's a lot of opportunity to do things that are going to help. For example, making more reliable detections of methane with MethaneSat. We are correlating their data with some geospatial data from Google Earth. And then you can understand if something is a plume, a real plume detection, or a bright surface on that spot. And that is one thing that stands on the way of holding companies accountable. If you don't have a reliable result and you don't know if it's a methane plume or a bright surface, you cannot hold them accountable. So we are hoping to make a lot more progress in TEMPO. What's important is they have the column density of pollutants. Nitrogen dioxide is really bad for health. And we know in which places is really bad. I'm sorry about that. But what we don't know is how it is distributed in altitude. If most of it is high in the atmosphere, it has concerns for global warming and for climate change, but not for health. So we are trying to do similar to what I just showed with MethaneSat, use other data to be able to resolve the altitude on these pollutants. So yeah, I'm very excited about Earth AI. Every time I talk about exoplanets, I feel the responsibility to say there is no planet. So let's focus on this one and try to save it. Thank you. And let's take it.
They use machine learning for climate projections. They train it on some climate model data, and then
They do, and actually, a lot of people are doing that. And actually, one good name is Viviana Guariba, who was who's at CUNY just here, and she was an astrophysicist doing machine learning, and she did a pivot. She took this pivot science fellowship, I believe, to transition to climate science, and she's doing great work. But yeah, a lot of people are doing it, and I think what I'm very excited about that are the physical AI simulations. Hopefully, will have an impact on this very complex modeling of the atmosphere. It's really hard to do, and they're very, you have to do simplifications, and hopefully that would help in that domain.
So this is a bit vague, but at the beginning, you sort of promised that we were going to be able to discover new physics, right? That we were going to be able to see new patterns that we didn't know about.
Yep.
And a lot of them, it felt like we already knew which parameters we cared about, and then we were trying to reproduce that. So can you speak a little bit on?
Yes, no, absolutely. There's two different things, right? And you're right. I promised something and then I didn't expand on it. I think both are important. I think just the unsupervised learning, there's not much that I need to do a new model for it. For unsupervised learning, you just have to do unsupervised clustering, and hopefully those will point to new things that you want to observe. For example, there was some examples that I was thinking today with the students, and it's like, yeah, for example, if you have outliers, you want to know where they sit comparatively to other observations to just see if they're interesting or not to follow up on. But mainly it's just a pointer. It's not a real machine learning model that we had to work on it for it to be more physical. I think this is a two-step thing, right? You want to identify things that are interesting, and then once you have them, you want to build models that are reliable and physical. And hopefully, so one of the things I'm thinking of doing and we're very interested in developing is tools that are not going to be just physical that you put there in the Lagrangian or whatever, but that you will discover it, like the Lagrangian neural networks. But by discovering symmetries, maybe you can discover things that you're not building in because you didn't know about. So that's another part of this AI simulations project that we're hoping to have that more exploratory side of things, and then trying to learn the physics from them. Does that answer your question?
How do you detect errors or error analysis in your AI training or your models? Like, how do you propagate the error?
Yeah, actually, it's not, you don't propagate errors like in a traditional simulation, right? Because you train end to end. So in the probabilistic models, you get the full posterior probability distribution. So that's how you get your errors, pretty much hoping that the full posterior is right, and you can test that, that how well you're doing on the posterior. So that's how you get the errors. So it's very different than the classical way of simulating things. It's not like you accumulate the errors. Then you can do the same with variational autoencoders. But if it's a deterministic, is a deterministic model, then you don't get the errors. You can just get ideas of how well you're doing by testing it in different scenarios that you know the answer for. And so you can get a measure of precision, but not really the errors.
Thanks, Cecilia, again.